My name is Brett Sheffield from the Webrtc project, and I'm here today to talk to you about IPv6 Multicast and the next generation internet. Now, the Webrtc project is now part of NLNet Foundation's NGI Zero program, which aims to build a better internet. And they have funding from the EU and other sources and are giving it out to projects like mine to try and fix and improve the internet. That may apply to your project. So if that's interesting to you, come and talk to me afterwards. And you may perhaps be able to get funding from them also. So before we begin, I need a volunteer. Now, I need a volunteer who, despite the coronavirus circulating around, doesn't mind shaking hands. Please come to the front. Because basically, I want to give you all a choice. We can do this presentation in a Unicast way, or we can do it in a multicast way. So to give you an idea of what that might be like, in the Unicast world, we begin a connection like this. We start with a coronavirus-free handshake like this. You didn't realize that we were gonna need to adapt the TCP/IP protocols to cope with this, but here we are. So basically, we start with a handshake in TCP, and the thing is, we need to maintain that handshake throughout the talk, which is going to be about an hour. If you'd all like to form a line behind this gentleman, then basically what I can do is deliver the talk to you one at a time, because that's how Unicast works. Now, obviously, we're cleverer than that in the world of Unicast. I can probably do two of you at once. Or you could attach to my legs, maybe four. That's probably about my connection limit, I'd say. And the way we do this is I'd need to repeat a few lines here, and then repeat a few lines of my talk here, and here, and here, and basically I'm doing this little Unicast dance, and it's great. But again, we're cleverer than that in the Unicast world, aren't we? We have CDNs, we have caching, we have all these sorts of hacks to get around the fact that fundamentally Unicast doesn't work at internet scale. So thank you. So can I have a show of hands? Who would like to do this talk in a Unicast way? Okay. Now in a multicast way, we have, well, there's always one. In a multicast way, we have other options. We can, by coming to this room, essentially you've performed a join on my multicast group. Thank you. There are other groups going on at the same time in different rooms. Multicast is not broadcast. You have chosen to come here of your own free will, presumably. So you have joined this group, and I am now delivering the talk to you all at once. And the great thing about that is the load on me as the speaker doesn't change. It doesn't matter whether the room is full or empty, if people come in late or if people leave, please don't. The load on me does not change, whereas when I'm doing that Unicast dance, the more connections I've got, the harder it is on me. I've got to maintain all of that state. So who'd like this in a multicast way then? Okay, well, I've got an hour, but you're all already convinced that multicast is better than Unicast, so I'm kind of done. But I have got more slides, so I'll carry on a bit longer. In 2001, RFC 3170 was written, and it says this: IP multicast will play a prominent role on the internet in the coming years. It is a requirement, not an option, if the internet is going to scale. Multicast allows application developers to add more functionality without significantly impacting the network. Now that was 2001. What year is it? So yeah, we've kind of not been doing a lot with multicast. It's not really used on the internet. It's largely misunderstood. Those who do know about it have quite a few misconceptions, which I'll come to later. But I'm here to tell you that multicast is more efficient than Unicast. that it's more scalable than Unicast, that it can solve real-world problems, that it has privacy advantages over Unicast, that it is the missing piece in the decentralization puzzle, and it can help keep this fellow, this polar bear, a lot happier at the same time. So, what is multicast? We'll start with a bit of a definition. You may have seen something like this before. If you've glanced at a university textbook or you've been working in networking for a while, you'll know that unicast is one-to-one. Yeah, we're all good with that? And broadcast is one to all nodes. Okay, not too useful on the internet, and it doesn't exist at all in IPv6. It's been replaced by multicast, which is one to all nodes. Yeah? That's what we've heard? Cool? Well, that's wrong. Basically, Unicast, you set the destination. In broadcast, you send to all nodes, but in multicast, you don't. You don't set the destination, you send to a group. So no form of IP multicast in use today do you set the destinations for multiple nodes. It's just not how it works. It's pub-sub. That's essentially, if you take anything away from this talk today, remember that multicast is pub-sub networking. It has nothing at all to do with broadcast. There's a fundamental difference between unicast and broadcast on one hand and multicast on the other, and it's this, that unicast and broadcast are push and multicast is pull. That leads to some interesting properties that you might not sort of notice if you're still thinking of multicast as one too many. It just doesn't work that way. You can't spam someone over multicast. If they haven't subscribed to your group, they won't get any data that you send. So, it comes to this philosophical question here. If a tree falls in the forest and nobody's listening, is any data sent? And in a multicast world, the answer is no. It's all dropped by the first hop router. It's all dropped by the switch using MLD snooping or IGMP snooping if you're still stuck in an IPv4 world. So that leads to some more interesting properties. We can send lots of data, but if nobody's listening, no data's sent. If this room was empty, then I can be talking away here, but nothing is ever leaving the podium. So that does lead to some interesting properties. There are a lot of misconceptions I come across when I talk to people about multicast. The first of which is that it's only for streaming. It's certainly useful for that. Or that it's no use for video on demand. That if everyone wants to stream something at the same time, that's great. But if they want to stream different films or at different times, then it's no use for that. I've heard that it's unreliable because it's based on UDP. I've heard that it's insecure, and I've heard that it can't work on the internet. Now, fortunately, that's all wrong. Multicast is essentially about group communication, and the funny thing about that is all communication is group communication. Even if I'm just talking one-to-one, that's just a very small group. I mean, that's the special case and the only case where unicast makes sense to use. For all other cases, multicast is better by definition. It's why we built it. Any shortcomings with multicast are a fault of the implementation, and we can fix implementations just like we've done with the many, many hacks that we've done with Unicast over the years to get it to continue to work and try and make it scale. So you are here, more or less. We'll sort of round the back a bit. And there. Hello. You're on this planet with approximately, if this coronavirus doesn't make too much of an impact, about 7.7 billion people. And that number seems to be going up rather than down. And all of those people want to communicate. And then there's the Internet of Things on top of that. That's a whole lot of nodes that want to communicate. So forgive my artwork, I drew this myself. These people, these nodes, communicate in groups. It might be your friends, your family, your colleagues, but perhaps not this guy over here. We communicate in groups. Our devices communicate in groups. It's how everything works. We don't build standalone applications anymore. But we come to the elephant in the room. I'm telling you that multicast is useful, and that RFC 3170 that we just looked at says that it's necessary for the internet to scale. But the elephant in the room is, if that's true, then how's the internet working at the moment? It must, we've got Unicast, we've got Facebook and things. It must just all be fine, yeah? There's no problem to fix, so we can just go on and ignore it. But I would argue there's a problem with Unicast, and it's this. Well, certainly this is one of the problems. This is one of Google's data centers, the Berkeley one, I think. We're building an awful lot of these. They draw a huge amount of power. Have a look at the substation in the foreground there. And you've basically got a huge number of computers all in one place, tightly packed in, just generating heat. That's what a data center is. And the reason we have so many of these things and we're continuing to build more and more of these things is because we're fundamentally working in an inefficient way. Efficiency matters. Every CPU cycle you waste, every byte you waste, is killing the polar bear. Essentially, Unicast leads to centralized designs. It's just what it does. To make it scale, to make it work, you need to centralize, and that's what we have now. Multicast leaves open the possibility of decentralized designs. But why does any of it matter, really? I think it comes down to this, which is the UN Declaration on Human Rights. We are exposing ourselves through massive centralization. If Snowden has taught us anything, it's that we can't trust sticking all of our data in one place. Collected data will at one point or another be leaked data. We think we're great and we have methods to secure things, and it's, we have the technology, but ultimately all these systems are built by humans. There is a strong desire to get access to data. If it's centralized and made easy, it will leak more easily. Our democracy today is under threat from a number of angles. It's under threat from criminals. Well, everything's under threat from criminals. It's under threat from corporations. Apologies to the sponsors of this conference who are on there, but you know what you do. And it's under threat from governments, the people who are supposed to be there to protect and serve us. And as Paul Vixie was saying in his talk this morning, they don't think of themselves as the opposition or as evil actors. They are doing what they do because they believe it's the right thing to do. I happen to disagree, and I think a lot of people in this room probably disagree that they are always acting in our interest. Efficiency matters, as I was saying. If you waste bytes, you are killing polar bears, you are building more of these, and this guy's getting upset, Greta Thunberg is getting upset, and you don't want that. So, I think it comes down to the reasons behind the internet existing, the design goals that we had in the first place when we designed the initial protocols and so on. Privacy and security weren't as big a deal back then. As an example, who here has ever administered a server over Telnet? Go on, yeah, don't be shy. We hadn't invented SSH, it's okay, We've moved on, but those are the protocols we're working with. We're trying to, patch these things now, retrofit security to protocols that were just not designed for 2020 and beyond. The design goals of the internet have changed. So let me talk a bit about multicast, that's why we're here. Brief history of IP multicast. The original multicast RFCs that describe the idea of multicast talk about multicast in the way I'm talking about it now. They talk about it being many to many. They talk about it being generally applicable. Unfortunately, when the very first RFCs, when the very first protocols were standardized in RFCs for multicast back in the IPv4 days, What they came up with was this, which is a very clever hack, but basically it's protocol independent multicast. What that means is that it doesn't matter which protocol you're using to sort out your unicast routing, we can make multicast work on top of that. We can use it to do loop detection and various other things, but basically it doesn't matter if you're using BGP or OSPF or RIP, it's independent of that. But I tend to call it unicast dependent multicast because it's the multicast you have, but it's dependent on unicast. You can't have IP multicast today without unicast as well. I'd like to break that dependency. To have multicast working on a local LAN, well, it kind of works by default. But if you don't have MLD snooping turned on, or in the case of IPv4, IGMP snooping turned on, then it's essentially broadcast. So the failure mode is at least that it works, but it doesn't work very well. For reasons I don't understand, MLD snooping is not turned on by default on switches. So if you want to deploy an IPv6 network, you need to turn on a setting on your switch. You need to turn on MLD snooping. It's just one setting, but if you don't, you're doing broadcast. It looks like Windows is running on your network. So why that's turned off by default in 2020, I don't know. We need to do something about that. And so yeah, on a local LAN, that switch is the only thing you need to configure. But what about getting beyond that first hop router? That's where multicast gets a little bit more complicated. We need, in some cases, rendezvous points to configure our multicast network. I'll explain a bit how that works. Say you've got Ubuntu 2 over here, and it wants to join a multicast group. So it sends a join message, star comma G. G is the group that it wants to join, and star means I don't care who's sending, any source. So this is any source multicast. So it sends a join, a PIM join towards its nearest router, which in this case is R5 here, and R5 says, okay, I don't really know what to do with that because I'm not aware of any multicast groups. So what I'll do is I'll forward that request on towards the rendezvous point, which is a pre-configured place on the network, sort of per ASN, which is just a place where packets meet up and have happy times. So the router 5 adds in this interface here, E02, into its outgoing interface list, just to say that somebody on this interface, I don't care who in the case of IPv6, it doesn't record your IP address or anything, it just says this interface has an interest in this group. So I'll keep a note of that and I'll forward the packet on. And you send on that join request towards their rendezvous point. Now that rendezvous point can just kind of ignore that really, because there are no senders yet. But if we have this Ubuntu 1 over here that wants to start sending some data to a group, then again it sends it to router 1, and router 1 wants to know where to send it to, so it sends it towards the rendezvous point. And now the rendezvous point has a source and a sink or a destination, and therefore we can build our source tree. And it's a little bit more complicated than that. There are multiple modes for multicast. There's bidirectional multicast and all sorts of different things, but essentially they all have this in common in the any source multicast world. There is, however, a simpler form of multicast, that's any source, which is single source multicast. Essentially, you're sending a join to group G, just as you were before, but in this case, you know who the sender is. You know who that source S is. You're saying, I'm only interested in this one IP address. And you can do fun things and combine this with Anycast, BGP tricks, and so on, to basically spread that across the internet, connect to a closer source, and so on. But single source is a lot easier to configure. So again, we've got Ubuntu 2 here that wants to join a group. So it sends a join, but in this case, it knows that the source is Ubuntu 1. So it just sends the join. There's no rendezvous point now. doesn't need one. It just sends the join towards towards Ubuntu 1. Again, all of the routers in between add that group into their outgoing interface list. So E02 here, E01 there, and so on. So if any other nodes join in up here or down here, this one joins in, then it just sends, it knows to send the multicast packets out both of these interfaces when it gets to this switch. So that becomes very simple. You've got single source multicast, you just have a join, and then the data flows. You've got your source tree immediately. You don't need to muck about with rendezvous points. And so for a lot of use cases, this is all you need. To have this work on the internet, you need to turn on one setting on each intervening router. It's just IPv6 multicast routing, and you're in business. There's no need to configure anything else. And basically every Cisco, Juniper, and other major manufacturer IPv6 supporting router on the internet has supported this for 15 years at least. Soho equipment, your home router, probably not. It's a struggle to get something that supports IPv6 properly. But certainly multicast is supported by just about anything you can buy that's a serious bit of kit. Now, who's played with multicast a bit? Who's worked with it before? Okay. And was that, keep your hand up if that was IPv6 multicast. So, nobody. Okay, yeah, that's what I tend to find. A few people have worked with IPv4 multicast. There are still people, for whatever reason, who are setting up IPv4 multicast networks, which I don't understand. IPv6 multicast is considerably improved over IPv4 multicast. And the first thing that's an improvement here is this address space. In IPv6, we've got 112 bits of address and 128 bits of address. 112 bits of that are available for multicast groups, which is a whole lot of bits. It means you can do some fun tricks, which I'll come to in a minute. Who's worked with the M-Bone? Does anyone remember that? Okay, one person. It's not really around anymore. It was IPv4 only, but essentially it was a backbone network of multicast that you could connect to. So if you had a bit of multicast running on your network, somebody else was doing something with multicast on their network and you wanted to talk to them, you could tunnel into that backbone and everything was happy. I think Rod Stewart famously gave a concert over the M-Bone, but it's not around anymore. There was another experiment in Brussels called CastGate. Essentially it was a browser plugin and some other bits and pieces. It worked in a similar way to the M-Bone. You, again, tunnel back to a backbone. Both of these things were mainly focused on streaming. You could do other things with it, but most people are thinking about audio and video streaming when they're thinking about multicast. CastGate's dead as well. It's been dead for 10 years now. As an ASN, as an autonomous system, if you run your own ISP essentially, then you have certain tunneling things available to you, like RFC 7450, which is automatic multicast tunneling. It works a bit like the M-Bone did. It tunnels together discontiguous bits of multicast network. So you can configure this on your router, have it connect to other routers. You can do tricks with Unicast for discovery and this sort of thing. So if you're in control of the router, then fine, you can set this sort of thing up. It's not much good if you're a developer though and you want to write a multicast enabled program. So we've still got a problem to solve. You might have control over your local router, but as a software developer you don't have control over all of your potential users' routers and all the ones in between. So this is not sufficient for our purposes. For a long time, I thought TCP/IP was going to be the blocker to multicast adoption, because multicast is built on UDP, and we have got a bit of a TCP/IP addiction. But fortunately, we're seeing now with Webrtc and QUIC, which is the basis of HTTP3, which is going through the standards process now, that's based on UDP. So if we can build the web on UDP, then that opens up all sorts of possibilities, which I'll come to again later. TCP, the reason we have it is because it lets you build a reliable network on top of a connectionless, unreliable network. It's why we built it. So if I'm gonna say let's use multicast, let's use UDP, we need to ask the question, are there other ways we can achieve TCP/IP-like reliability? And the good news is, yes, we can. So there's an RFC for some of them, Pragmatic General Multicast, PGM, RFC 3208. It's an experimental RFC, and it's not really an RFC you just kind of sit down and implement end to end. It's not like WebSockets or something where you just kind of go, yeah, must do that, should do that, right? It's kind of a toolkit of options. At the basis of it, it uses NACs and replay. So if you're familiar with Unicast and TCP, I'll send a packet out to you and you'll send me back an ACK, and then I know you've got it. That means I'm responsible for your data receipt. In the multicast world, that doesn't really work. If I send out a packet to all of you and you all send me an ACK back, that's probably going to DOS me. If I'm talking millions of nodes, that's definitely going to cause a problem. So what we do instead is I send you, packets 1, 2, 3, 5, and then you go, oh, hang on, what happened to packet 4? And you can just send me a NAC one-on-one saying, I didn't get packet 4, can you send it again? But we've got other options as well. You don't need to send that NAC to me. You don't need to send it to the source. You can just turn to your neighbor and say, did you hear what he said? And they go, yeah, he said multicast's great. And you're like, okay, cool, well, I've got that bit of data now, and you didn't have to apply any additional load to the source. So that's one of the things that we don't have to. We've got a better way. There are a lot of efforts to decentralize the internet and to build multicast applications, things like chat and so on. IRC, Slack, Mattermost, all of these, Rocket Chat and so on, are all built in a multicast fashion, but they're all built up here at layer 7. We can do multicast down here at layer 3. It's a lot more efficient. So, and efficiency means, we can build probably 1/10 as many of these. I think there's billion-dollar reasons to be really seriously looking at multicast. And that's going to make that fellow a lot happier. So, let's have a look at some multicast party tricks. Video streaming, that's not really a party trick. That's what everyone thinks of when it comes to multicast. And I'm trying to change that. Sadly, the way I'm trying to change that is by building a video streaming application, but that's just a little confusing. That's what they gave me funding for, so that's what I'm doing. I'm building a decentralized, federated streaming application. Think of Twitch TV, but federated and decentralized. That's what I'm working on at the moment. And that gives me the excuse and the funding to build all of the underlying libraries that we need to bring multicast to the entire internet. We can also do video conferencing, which is many-to-many. It's the next logical extension of the previous. Replication, you're sending data to multiple locations. Why do you want to send that data more than once? It's as sensible as me giving this talk to you one-to-one. Again, like replication, consensus, things like Paxos, they have multicast modes that we can use for data replication and so on. Syslog, here's a crazy application of multicast. You want to do some logging at different log levels. We use a different multicast group for debug and for info and so on. And if you want to run a debug session on another server, you just tune in to the appropriate groups that give you the information you want. You don't need to bother that busy, expensive server that's doing what it's doing. It's just sending all this stuff all of the time. If it's not needed, no data is sent. It's perhaps a frivolous use of multicast, but it works. So I was sitting listening to Paul Vixie's talk this morning about DNS and the history thereof and the problems with it. I didn't quite have the courage to walk up to him and say, what I'd really like to do is get rid of DNS entirely. Let me destroy your legacy, sir. But in the multicast world, we don't necessarily need it. What's the purpose of DNS? Anyone? Correct. To translate human-readable addresses to IP addresses or, machine-readable addresses. That's what it's there for. Well, if that's the only purpose of DNS, then let's have a look at what we can do with an IPv6 multicast address. We've got 112 bits of address. So let's see, for an IPv6 multicast address, it starts with 8 bits that are all 1. So that just says this is multicast. Then we have 4 bits of flags and a scope, which is another 4 bits. E means global. And then the rest of those 112 bits are available for the group address. So that's a whole lot of bits. That's enough bits for every atom on Earth. So we can do things like this. Take a hash of whatever your domain is, squeeze out 112 bits, tack an FF1E on the front of it. You now have a global address, and there's been no central server consulted at any point. We've just got an RFC describing it. We can all agree on where example.com is. What's the need for DNS? Now, this is a very simple example. We can do more complicated things. There's all sorts of fun stuff you can do. Military-style channel hopping and all sorts of fun things in your application if you want. But at the most basic level, this works. And I use this in a couple of applications. So yeah, there's example.com now. It's just a SHA-3 address, 112 bits, which is collision-proof for our purposes, and FF1E on the front. Let's have a look at a chat system that I built. So we've got here just a very simple forking HTTP daemon, yeah? And it's built using the Webrtc libraries. And we then plug that into a local tap interface. So it's just a virtual interface. It's not plugged into a real network at the back. The front end is plugged into the internet, and you have a client connection come in here. So just a little bit of JavaScript running on top of the Webrtc JavaScript libraries, and it sets up a WebSocket. And now you've got a chat client in your web browser talking over just normal Unicast HTTPS to a forking web server. So, well, that's not very good talking to yourself. Let's get some more in there. So now we've got 3 nodes all talking to this chat application. And this is all just running through a virtual bridge here, but it's running through multicast. Think IRC, but every one of those channels, you know, if you want to join hash Finland, as I used to do back in the 90s and try and practice my non-existent Finnish, then you just take a hash of Finland, tack an FF1E on the front, and off you go. So you've got an entire chat application here running. Now this is just one server, but it's taking care of all the channel management for you in the networking stack. So this is a use case, a practical use case for multicast, where, you know, we're not talking across the internet, we're not talking across the data center. This is never even leaving the Linux kernel. This is multicast talking to itself. But what if you then plugged that virtual interface into an actual multicast network? Well then, you know, you can stick in your GitHub webhook, and it can be, you know, you can receive information here, and, you know, the fact you've pushed a change can get posted out to all these people who are listening here. You can have various other apps, or you can do this. What did we do there? We've basically federated 2 chat servers there with 0 lines of code. None. It's all taken care of at the network layer. I was pretty pleased when that worked. I was quite stunned when it worked, but yeah, we've got federation. And the chat applications that are out there today are doing this with thousands of lines of code. Multicast lets you build applications with a lot less effort, because essentially all these things are group. So if you've got a chat server here in LA and a bunch of us talking on the Scale channel, and you've got a bunch of people over here in Tokyo, if none of them are on the Scale channel, then no data is sent across here. And you are doing absolutely no work to track that state whatsoever. You've written 0 lines of code to deal with this federation. But the moment one of these people joins the Scale channel and starts trying to receive a video feed or just join in on the chat or whatever, the data will be sent across, but just one copy, no matter how many thousands or millions of people in Tokyo have decided to join in. It's just automatic. You don't need to worry about it. This is what a... Sorry?
A question, if I may. Or
can I take them at the end? Okay. There's a... this is what the Webrtc API looks like. If any of you have worked with 0MQ, it's deliberately similar. I was building it and I realized how similar it was to 0MQ, so I made it more similar. Essentially, you're creating a context, creating a new socket, and then binding one or more channels to that socket. And then you can send and receive messages. It's very simple. Here's another example, another application example. That's just sort of the main bit of it. I built an IoT updater. I'd been talking about it a bit. I thought I should show me the code, so to speak. And so the server for this IoT updater is 90 source lines of C. That's just the middle event loop there. Yeah, the client isn't much bigger. The only reason it's any bigger is because I put an extra thread in to do some checksumming, and that was a bit more efficient. But basically, it's a tiny little thing. It's up there on GitHub just to prove the point that I'm making, which is that we can use multicast for practical real-world things. If you control the network and you want to update a bunch of IoT nodes, which is, you know, essentially sending a file out to all of them, it doesn't matter whether you've got 1 or 1 million, you can use a method similar to this. So if we send out a UDP datagram, and each datagram contains a checksum of the whole file, it contains the size of the file, contains the size of the chunk of data that you're sending right now, contains the offset of that chunk of data from the beginning of the file. So 0 means this chunk goes at the beginning. And obviously a bit of data itself. So if you want to send an update, then you can do it like this. Now, we receive a datagram, and it's got an offset of 0 and a size of 4, so it just goes in there. And then we receive another one, and it's got an offset of 4, so we just plonk it in there. But this is UDP, of course, so these packets could arrive in any order. We don't know, but we also don't care. We've got the offset, so the data arrives, and we just plonk it in, stick it in any old where. And when we've got enough data, we go, okay, well, we've received enough bytes. Let's run a checksum. If that matches, we've got our update. And we've updated 1 node, 1 billion nodes. Doesn't matter. And the load on the server did not change. The server had no idea whether anyone was listening at all. So imagine a web server that worked like that. Imagine the entire static web working like that. If you sent a file on a multicast group, you could have the entire static web working like this with no need for caching, no need for CDNs, and the load on all of those web servers being completely independent of how many clients are simultaneously downloading. I think that's pretty cool. I think it's worth having a look at. You know, you go through and build your shopping cart up on a website, and you're building all that state locally in your browser, and then when you finally want to check out, then you need to talk one-to-one to the server, but not before then. The only reason you're doing it before then is so that Amazon and so on can track you. But what about flow control? What about reliability? This is UDP. One thing we can do with flow control, what I mean by flow control is essentially if you're all on different networks with different speeds and I send that data flat out to you, some of you are going to have a bit of a problem because you won't be able to cope with that data arriving at that speed. So I could send it really slow, but that's going to annoy those of you who are on, you know, big internet connections. So here's a thing that Unicast can't do that Multicast can. So we're sending our packets on group G1 here, which is a multicast group, and we just send packets 1, 2, 3, and 4. So what happens if that's too fast for you? What if we did this? Split the packets over 2 groups. So if you are on a fast link, join 2 multicast groups and get all of the data as fast as it'll come. And if you're on a slow link, just join one of the groups. Well, split it across 4, split it across 100, it doesn't matter. Remember that tree in the forest. If nobody's listening, no data is sent. If nobody's listening to G4, that doesn't happen. So this is one way of doing flow control. We can do crazy things. I mean, I'm not saying this one's a good idea, but you know, you could do this. For retransmission, you've sent packets 1, 2, 3, and 4. Well, if you missed a bit, you could actually just join group 2 and get it a little bit delayed. It's like pressing the red button on your TV or whatever to just skip back a bit in time. You can do this sort of thing for video on demand. So if you're running, you know, if you're watching a video, if you all want to watch it at the same time, well, great. But if you want to watch it at different times, what do? Well, we could pick a movie at random and we could play that once per hour. And that's great. You can watch it. As long as you tune in at the top of the hour, you've got the whole movie from start to finish. Well, we could have 2 channels and we could start every half hour. That gives you a bit more flexibility. Or every 15 minutes. And so how many channels do we need to have running in order to be able to do video on demand at sort of Netflix kind of scale, which is what, 25, 30% of internet traffic, I'm told? You can have everyone watching one of these possible streams. For a popular movie, you have lots of them. For a not so popular movie, you can, you know, have it a little bit less often. They're going to buffer in a couple of ads at the front anyway, so you don't have to have it exactly to the second starting at the same time. It's something we can do. Webrtc is a video streaming protocol built on top of UDP. It's available in pretty much every browser now. replaces old, simpler systems, and it does some interesting things. It's a complicated diagram, but it's not as complicated as it looks really. If you've got essentially 4 servers here, and they're all federated using something similar to that chat system I was talking about earlier, and you've got a source here sending video, yeah? Now what Webrtc does with simulcasting is it lets you send more than one quality stream at once. So what we've got here with those 3 colors, if I've got enough battery for my laser, there we go. We're sending 3 different colored streams of data there. The way that Webrtc simulcasting works is basically it sends one basic stream of data, and then if you want a higher level of quality, then you get the extra stream on top of that and build that on top of the first one, and add in the 3rd layer for full quality. Essentially with audio and more or less with video, if you want a lower quality stream, you just start dropping some packets. We do it all the time with voice over IP and so on. If packets get dropped, there's no point sending them later. You don't do voice over IP over TCP because a late packet is a useless packet. So in audio and video streaming, we can just reduce the quality, and the way Webrtc does that is sending these 3 streams. But then what happens? You've got media servers here that need to distribute this to everyone who's interested. So you've got all of these Chrome browsers sitting here wanting to tune in. And you know, this could be something like Twitch TV or a YouTube live stream. So you're streaming away here, these people want to tune in and they're connected to different servers. These servers need to keep track of state, need to keep track of who is interested in which quality level. So, you know, you've got someone here who wants full quality, you've got somebody there who's on a low quality. You know, they're on a poor link and they just want the simplest video stream. Then that all needs to be kept track of by these media servers. But not in multicast. I think you've probably caught up with me by now. We can actually just send all of these streams all of the time, and they will go to exactly which media servers need them. There's nobody joined to this one, so no data's going here. With this one here, all 3 streams are going and they're being distributed to, you know, everyone who needs it. This media server here is only getting the lowest quality stream because it's only got one client who's only interested in that. And that's all automatic, all at the network layer, just like the chat server we were talking about earlier. HTTP 3 is built on top of QUIC, which is UDP, and that got me very excited. If you can do it with UDP, can you do it with multicast? So I did a bit of Googling around, and I'm not the only one to have thought of this, which is nice. The BBC Research Group in the UK, there's actually a more recent update, they updated this in February, are standardizing now, putting through an RFC now, that does HTTP over QUIC supporting multicast. Now that's so they can do their video streaming platform and so on, but if they can do that, we can do lots of other things. We can have a multicast web, just like I was talking about a minute ago. I think that's pretty cool. So that comes to my project, Librecast. I am trying to get multicast working across the internet and in the hands of developers. So it's great, we've got things like AMT if you're an autonomous system, but I want you to just be able to basically hash include the Librecast libraries and start writing multicast applications today. So how am I doing this? Trying to get it into the hands of developers. I've built a simple multicast library. The next step is to expand that into more of a messaging library, a bit like ZeroMQ. I have a transitional tunneling technology that I'm working on, which should be available mid-year. It's required for the project I'm working on. Again, I'm not bringing you new stuff. This is 30-year-old technology. I'm just trying to bring it back. We can do this. Tunneling multicast works. We proved it with the MBone. We proved it with Castgate. I just want to bring it up to date for the IPv6 internet of today. And I'd like to develop an improved routing protocol that isn't dependent on Unicast, and I have somebody working with me on that. and then to work with all of you guys, all of you fine folk, on your projects to enable multicast everywhere it can be. Unlike IPv6, which I love, but I have to admit is essentially just a bigger namespace, multicast brings with it significant advantages over Unicast. And people ask me from time to time, well, how are you going to get multicast out there if we've kind of failed with IPv6? It's taken 20 years and it's still not everywhere. How is this going to work? Well, I think multicast is the way we get IPv6 everywhere, because it gives us things that you just can't do with Unicast. Well, I hope I've showed you that. I also want to make sure that new standards, such as Webrtc, support multicast from the outset. Webrtc is great, it's built on top of UDP. However, because the encryption was mandated as part of that protocol, it mandates a sort of one-to-one Diffie-Hellman style key exchange, which isn't compatible with multicast. We need to use group keys and capability tokens and things like that in the multicast world because we're not talking one-to-one. So I think we can fix these standards and we can make sure that new ones aren't broken for multicast. So that's me. I have no idea where we are with time, but if anyone has any questions, I'm happy to take them. Please, you are.
So my question is, what about security? We need to have authentication, authorization, and how does this apply to multicast?
Okay, well the question is, what about security? We need authentication, authorization, and so on. How do we apply this to multicast? And the answer is more or less the same way we do with Unicast. All of these things are available to us in the multicast world. We can use exactly the same protocols that we use in the Unicast world. In some cases, that's going to break our scaling, and then we will be no worse than Unicast, but no better, and that's not good enough. But we do have things like group encryption keys and so on. We do have things like capability tokens. There's quite a bit of work has been done on group encryption schemes and so on. Not as much as on one-to-one, which is one of the reasons why I'm traveling about talking about multicast, is I want to get more people working on it. There are problems to solve, don't get me wrong, but we had a lot of problems with Unicast and we still do, and we fixed them. Multicast has challenges to overcome. There's been a certain amount of research in different areas, but we need more. I need security experts to come on board and join the project and say, right, yeah, can he do that? That's not going to work. But it is certainly possible to build a secure multicast network. Does that answer the question? Mm-hmm.
Networking layer. So do you envision that this will add lots of load to the network stack? Because there's a reason why we use the application level, right? So there are lots of things we already have. And then if we move that to the communication level, to the network level, that will require lots of additional infrastructure as well, right? Routers and stuff like that.
Okay, well, let me summarize that. Essentially, if we are taking a lot of the work from, that we're normally doing at layer 7, the application layer, and we're pushing that down to layer 3, the network layer, as I'm proposing, is that not going to create additional load on routers and such? Is that going to cause a problem? There's a reason why we do this at the application layer. Well, essentially, yes and no. Yes, it is going to create additional load on routers and so on. Not as much as you might think. These things have been tested at some scale. And these routers are doing quite a lot of work maintaining Unicast routes at the moment. A lot of that work can go away, but ultimately, I'd love to see Unicast disappear along with IPv4, but that's a way down the track. So routers can cope. It is additional load. hardware is getting better, and we can build more efficient protocols, which is going to make that a little bit easier. Multicast routing is, in some ways, simpler. It can be. I mean, you're not having to keep track of as much in terms of lists of routes and so on. You are essentially keeping track of interfaces that are interested. You don't really care who out there is interested in a particular group. So, any other questions?
Yeah, it seems like if you want to sell this, you need to sell it to Netflix, and if they adopt it, then you can succeed. But why can't you make a pitch to Netflix if this is better? What about Netflix's architecture already gives them the benefits without the expense of this experimental protocol, when they can be caching things out to the edge of the network and have a distributed set of CDN caches, and that seems to be working well enough for them. They should be on board with you if it was a benefit.
Well, I'd love them to be. So basically, I should be on board with Netflix because there's obviously a big advantage for them using it. Yeah, essentially, Netflix is one user for this. They're not the only one. Video streaming is one thing where there's a significant advantage from multicast. Why are Netflix not using this? Well, they may well be using this inside their network in some places. And as I pointed out, the BBC Research are looking seriously at multicast and investing resources in that. Because even with CDNs and so on, you've still got a lot of load. You've still got to get data out to those CDNs. And doing that over Unicast is senseless. You're sending the same data more than once. So what I understand the BBC research stuff is trying to do is trying to make it more efficient getting out to the CDNs. Getting it beyond that, well, it's going to save them a lot of resources. CDNs are expensive. So they've got a solution at the moment that more or less works for them. But I saw a tweet by LUNAP late last year, the London Access Point Exchange, basically. You know, there's a lot of these peering points around the world in major cities. And LUNAP tweeted that they'd reached a peak level of so many bits per second that they'd never seen before. And that was entirely due to a football match that was on. That's ridiculous. That's a case where a lot of people are watching the same video at the same time and they're hitting peak loads. Well, as I've just shown you, you don't need to do that. In the case of video on demand, we've got lots of improvements we can do too, but there's still a significant use case just with the live streaming stuff. This is one of the reasons for tackling that first. Please. If everyone turned on multicast routing today, which is, say, is one setting on every router, then yeah, we could be using it now. It's there, it's supported. It's not necessarily supported in your home router, but very little is. That's fairly easily fixable. A lot of people are, for video streaming and so on, buying a little dongle, a little box from Netflix and Amazon and so on, and plugging it into their TV anyway. So what I'm proposing, in addition to the multicast libraries, is to have a small router system. I was actually looking at one of the little boxes that was out in the exhibition hall here as a possible starting point. So we can do this using a tunneled system as a starting point. But essentially what we've got is a chicken and egg problem at the moment, in that multicast isn't supported on the wider internet because nobody's using it. Nobody's using it because it's not supported. We need to break that cycle, and I think the way we do that is with a transitional tunneling system where we demonstrate the use cases, the utility of multicast, and then create the demand so that we can persuade service providers to turn it on. And obviously if we've got Amazon and Netflix and Google saying, please turn this on, then it's not just me saying it, it's people with billions of dollars saying it.
Are those companies saying turn it on right now?
Some of them are looking internally at multicast. I don't think anyone's saying turn it on the wider internet at the moment. But as we've seen with QUIC and HTTP 3, and before that with Speedy and HTTP 2, when you are a dominant global player and you control the main browser that everyone uses, and you control a lot of the servers, and you sit on the standards body, you can kind of do whatever you like. And so if Google wanted this to happen, then they could make it happen. If Netflix wanted this to happen, it would happen. So my job's to persuade them that this needs to happen.
So my question is, which I think you answered, I just want to clarify. Do the peering nodes have multicast enabled or not?
Do the peering nodes have multicast enabled? Some of them do, some of them don't. You can use things like AMT at that level to tunnel between routers if you need to go through an area that doesn't support it. Getting it supported, it works in the data center. You control things there, and there are lots of use cases there where you can get benefits. I would say there's use cases for multicast where it doesn't even leave the Linux kernel, but that was just me being silly. Getting it working on the wider internet is, I accept, a big challenge. I may have bitten off more than I can chew, but if anyone wants to help me digest that, then please come and join me and help me fix this broken internet. Please.
One thing I'm not understanding when it comes to how you can set up many channels for it.
Mm-hmm.
One of them having turned on or said I want to go onto the channel at one time, and another one coming on a minute later saying I want to get on. Would it not have to send through the data that it previously sent to the other device if it's streamed content? Anyway, right?
Okay, well, if you are joining a group and another device joins a bit later, and you're in a streaming situation, would you not have to repeat that data? Well, again, it depends on the application. If it's live streaming, well, you've missed it. If it's video on demand, then in the case of popular programs, there's going to be more than one person wanting to watch that at the same time. So, if you're tuning in a little bit later, yes, the data is getting sent again, but it's probably getting sent to more than one person at that point. So it depends. There's a lot of cases with multicast. I mean, it's true in programming generally, but there's a lot of cases in multicast where there's no real one-size-fits-all solution for every possible application. What I'm trying to build is a sort of toolkit and a set of standard solutions, show how multicast can be used. I'm not going to try and solve every use case, but I'm going to try and provide the toolkit so that when you build your application, you decide what you want to use. Am I going to use forwards error correction? If so, how much? Because you've got options with that. But to give you a standard set of tools that make it easy so it at least works. And then, just like with every other programming environment, you need to tune and think about what you're developing. Any other questions before we take it to the corridor? Oh, the back.
If I understand your description correctly, when you join the group, you're effectively informing all the routers on the path that you want the packets to.
Yeah.
But there's no information that goes to the other ends or the members of the group that says someone joined. Is that correct?
Okay, so basically when you're joining a multicast group, you are sending a PIM join to your local router, and that's propagating on. Is there any information that gets sent to members of the group to say somebody's joined? By default, no. So this is the thing, I didn't really mention it in the talk, but one of the privacy advantages of multicast is if you join a multicast group, no state information goes back to the source. So one of the advantages of building the web that way, for example, or building a chat application that way, is you have no idea who's listening unless you build it into your application. There are cases where you want to. If you're building a centralized corporate application, you want to know who's on, and we've got all the authentication tricks there that we have with Unicast. But in the case of the static web, where we are increasingly getting sensitive about tracking and so on, there's no destination address on a multicast packet. There's a source address for the sender, so you know where you got it from, but there's no destination address. Ideally, I'd like to get rid of the source address as well, but we'll get there in time. So there's already a privacy advantage with multicast, not having that destination address, and we haven't even done any work for that. That's just how multicast works. So in the case of streaming something now, people can see, somebody on your network could see what you're streaming potentially. In the case of multicast, well, if they're on your local network, then they're in kind of the same position they are now. But if they're anywhere else beyond that first hop router, then they don't know where that data is going. As the source, you have absolutely no idea. You don't even know if anyone's listening. In single source multicast, there's ways you can tell at least somebody is listening, but you only know it's one or more nodes. In the case of every hop beyond that, the data is getting sent to the next router and it's sending it out of whichever outgoing interfaces are in its list, and it's just getting passed on. You don't know where that data is ultimately going. So we've got wonderful solutions like Tor and so on in the Unicast world, but these are hacks built on top of Unicast to try and make it secure and private. And we need these things, but we are starting with a serious advantage in the multicast world in that we're not trying to make up for inadequacies in the protocol. I mean, not having a destination address is an amazing advantage. So you can still build something like Tor on top of it. You can build decentralized mesh networks and peer-to-peer things and so on top of it. Peer-to-peer and multicast have a lot of things in common. They can learn a lot from each other. So yeah, it's a rich field for research for anyone who wants to get involved. There's a lot of, it's very easy to get to the bleeding edge in multicast. Anyone who's worked with IPv6 will know that 10, 15 years ago you didn't really have to work very hard to find things that were broken and find interesting solutions and so on. In the multicast world, we are in those Wild West days. There's a lot of stuff that just hasn't been properly thought about. A lot of advantages I'm discovering that people just don't seem to have stumbled across, and problems that need solving. So yeah, you can stay in the Unicast world and you can find really hard corner cases and so on that nobody's dealt with, or you can come to multicast and help me make it better, and I trust you. Trust me, I can find problems for you to work on that without really trying very hard. Anyone else? Okay, a question is how much of this is possible today without getting everyone to reconfigure their routers? So right now today, there is a LibreCast library there that you can just hash include in C, and that will let you build a multicast application that works on your network where multicast works. It just makes it easier to build an application. By mid-year, I'm expecting to have the transitional stuff working and working with the streaming application to show how it works, with other demonstration applications to follow. The aim is to get those that C library into Python, Ruby, whatever you want, so you've got it available in your language. And if you want to help with that, again, come and see me. So yeah, multicast today doesn't work on the internet without setting up some sort of tunneling. You can set that up manually for your own cases, you can set that up with AMT if you control the routers, or you can help me and we'll make it available to everyone by just including a programming library. Up the back.
This isn't much of a question, but more of something that I just thought about that might be interesting. So basically, how feasible would it be for, let's say, a company to get a bunch of addresses and provide a service where when you want a specific file, you would tell the web server using Unicast, I want this file. It gives you a specific address, and it starts the broadcast when you answer it. That way, you have all these addresses that are that could be kind of streamed to on demand without having to wait for the next replay of that file. I think that would be really interesting because that way you'd be able to use multicast for very specific things, and at the same time, you could also have a section like addresses that are just dedicated to always replaying the same file. I mean, I guess that kind of.
Yeah, I mean, essentially you can take a hash of the file that you want to distribute, and that can be your multicast address if you want. So in the case of a web server, that's one way of doing it. Connect to the server. If you've still got a unicast world happening, you can look up using DNS to find out where the source is for that, and then you can just download all the data over multicast. Connect, get an index file, and that tells you all the hashes you need, and then you just get them all on channels. I'm planning on building a demo of that quite shortly, actually.
Because just thinking about this, I mean, it's super, super useful, especially for hybrid environments. You take care of all the static stuff, like I said. Using multicast, any application logic, you can even call it serverless, so we can, make more people interested in it, and all the application logic is done by our serverless platform, and all the static stuff is given by multicast. And I mean, that's pretty interesting.
There's a lot of really exciting applications for it. Just the more you think about it, the more you find. There's not enough people thinking about it, and it's kind of the internet upside down, just given that it's pull rather than push. So it really bends your head when you start trying to think at the scale that multicast could potentially work at, and try not to break that ability by doing your unicast habits. It does take quite a shift in thinking to be able to start building multicast applications. It's not just, one too many, which is what we've all been told. It's a fundamentally different way. So, as I mentioned earlier, it's essentially pub-sub networking, publish, subscribe. So, if you take one thing away from that, that's what multicast is. It's nothing to do with broadcast. It's pub-sub networking. Okay. Well, thank you. Thank you very much for coming.